All right, hey everyone. Good afternoon or good morning, whenever time you're watching this. So just a disclaimer, this is going to be kind of a long video because we have a lot to cover in this lesson. Today we're going to be talking about composition of functions. Your aim for today is how do we combine functions and find their domains. Okay, your homework is homework number 11. It's going to be in the OpenStax textbook, page 60 to 61, numbers 9 through 19 odd, and then followed by 25 and 27. Okay. For the objectives, this spans not only this lesson, but also the homework. So there's like a few other questions that are covered in the homework that we won't really get to here, but you'll be able to solve it based on what we learned in this lesson, okay? But yeah, your objectives are gonna be find the sum, difference, product, and quotient of two functions and their domains. Second, we have explain how the domain of the quotient of two functions is different from the domain of the sum, difference, and product of two functions. That's followed by find compositions of functions and their domains. Find compositions of more than two functions. Okay, so like we'll be looking at the composition of three functions. And then lastly, we have find the original functions given their composition. Okay, this last bullet point you'll see in the last question, I believe it is, in the homework. So question number 27. Just keep that in mind. Okay, for the do now, it says Mr. Kennedy went shopping at Staples with two coupons, a 20% off and a 15% off. Let me zoom in here. So just to save time, I won't be going to the slides as much as I can. But yeah, so I'm gonna just show you here. Assume he buys a chair for $100. Does the order in which he applies the coupons to his purchase make a difference in his final spending amount? Try to incorporate functions into your answer. Okay, for answer, that's gonna be, so if you apply this 15% first, that's noted by here like 0.85, right? So 0.85 of a number, that's going to be 15% off, right? So 0.85 times 100, that's $85, right? And then if you then apply the 20% coupon, 20% off coupon, I should say, that'll be 0.8. And then in total, that'll be $68. If you apply the 20% first, so that's denoted by this number, like 0.8 times 100, and then you get 80, right? And then 80 times 0.85, that will also be 68, right? And yeah, we know like intuitively that this shouldn't matter, right? Otherwise you see people like, wondering like which coupon should I apply first at the store, right? And that would, take more time. But, in this case, it actually doesn't matter which coupon you apply first, okay? As for applying functions or incorporating functions into our answer, you can see it like this. So f of x equals 0.85x, that's the 15% off. And then the 0.8x, that's the 20% off, right? So if you do g of f of 100, right, that'll be 0.8 times 0.85 times 100, right? So f of 100, right? So f of 100, plug in 100 to here, right? So it's 0.85 times 100, that's this inner portion here, right there, right? That inner kernel. And then after that, you apply g, right? The function g. So g is just multiplied by 0.8, right? So that 0.8 comes after. And our question is, does this match up with f of g of 100, right? If you switch the order. And as we just saw, it does match, right? So f of g of 100 is the same as g of f of 100. And g of 100 is 0.8 times 100. So that's that inner portion right there. And then if you apply f to that, you'll get 0.85 times that, which is both $68, right? So in this example, the order does not matter, okay? We're gonna see an example, when you compose functions, which is our aim for today. When you compose functions, sometimes it does matter, okay? So in this case, it doesn't, but yeah, sometimes it will, okay? All right. But segueing into the first topic for today. So today we're going to talk about the sums, differences, products, and quotients of functions. And then next we'll talk about the composition of functions. So actually the do now was an example of a composition of functions, right? Combining two functions to create a new function. So evaluating one function first and then plugging that result into another function. Okay, so that's an example of a composition of functions. Okay, but yeah, let me get to the first topic for today. So functions can be combined to form new functions f plus g, f minus g, f times g, and f divided by g, similar to the way we add, subtract, multiply, and divide real numbers. Okay, nothing really groundbreaking here, just, yeah, something you can do, right? And just as a follow-up question, given f plus g of x equals f of x plus g of x, what happens if the domain of f is a equals 0, 1, and the domain of g is -2, 1? Okay, so the point of this was that these do not overlap, right? So 0, 1 does not overlap with -2, 1, where this is exclusive of 1, right? So the answer to that was f plus g is not defined. The domains have to share some elements in common, right? So you wouldn't be able to plug anything in, right? Because there's no overlap. Now, just note that this question, I didn't really expect you to use any like mathematically robust concepts. This is just like kind of like using your common sense. But yeah, just to allude to the domain of functions when we're summing them up. But yeah, let me get to that here. So here's what I wanted to really say. If the domain of f is a and the domain of g is b, then the domain of f plus g is the intersection. Okay, so if you remember this symbol from geometry or algebra 2, this is the intersection symbol. Okay, so a intersect b is where they overlap. Okay, and you don't have to copy any of this down. I'll get to the slides where we have to copy something down. Okay, so let me jump to that now. Okay, so here's the first thing I want you to copy. Okay, I know it's a lot, but yeah, it's actually conceptually simple. Okay, so algebra of functions. Let f and g be functions with domains a and b. Then the functions f plus g, f minus g, f times g, and f divided by g are defined as follows. Okay, so if you have this, you just add it separately, right? And then the domain is the intersection of a and b. Same thing for subtraction, right? Just subtract the function separately, domain is the same as this, and then multiplication is the same. The only thing that's different is the division of functions. Here, I know this looks complicated, but it's actually not that bad. So it's just x is an element of, okay, so remember this epsilon symbol means element of the set of intersection between a and b. Okay, so x is an element of the intersection between a and b, such that g of x is not equal to 0. Okay, so it's basically this first half of this bracket is this part. So it's these three, right? That's the same thing. But we have an added condition that g of x can't be 0, right? Because, right, g of x is in the denominator, so we can't have that be 0. Otherwise, it will be undefined. So we just have that extra condition for the division of functions. Okay. But yeah, if you need a copy of this down, please pause the video here. Otherwise, I'll be getting back to the lesson. All right, so let me go back to this part. Okay, so this is where we left off right here, the notes. And then actually, this would be a good time to show you the rest of the lesson. So as I said, it's kind of long, and I apologize for that, but yeah, just the first half is pretty intuitive, it's like this, right? And then secondly, we have composition of functions. But yeah, I just wanted to combine these two topics together since they relate. Okay, so first we're going to jump into an example. It's kind of long because there are a lot of parts, but it's pretty simple. After the example, we'll talk about the composition of functions, and then I have this picture of a cronut here, which I'll explain in a bit. And we're going to dive into the concept of composition of functions. So there's the definition, and then you have our classwork. Classwork is kind of long too, but yeah, there's a lot of questions that can be asked with regards to this topic. So that's why it's long. But yeah, nothing we can't handle. We'll get back to the classwork after we go through the lesson. Okay. All right, so regarding the lesson, here was the example. Okay, so let f of x equal 1 over x minus 2 and g of x equals square root of x. We're going to find these, these four combinations that we just saw in the notes and their domains. Okay, and then part B, we're going to find f plus g of 4 and then f divided by g of 4. Okay, so we're going to skip these two, right? The difference and the product. Okay, but here I have the solution that's provided by our textbook. This is the old textbook that we would normally use in pre-calc. Yeah, just FYI. Part A, so the domain of f is x is not equal, x such that x is not equal to 2. So that's this part, right? Okay, so x can't be 2 in this function. And the domain of g is x has to be greater than 0. Okay, so that's that square root function, right? It has to be positive or 0, right? Otherwise, you're going to get complex numbers, which we can't allow in the domain. And then the intersection of the domains of f and g is x such that x is greater than or equal to 0 and x is not equal to 2. Okay, so as you can imagine, right, you can notate this as, right, so you have 0 here and then 2, right, so that'll be this part. Anything above 0 is okay. So that's this part here. And then it can't be 2, right? So we're gonna have an open circle there. So as you can see, your interval notation is gonna be 0 to 2, inclusive of 0, right? That's this part here, and then union 2 to infinity. Okay, that's the interval notation. All right, and then the sum, difference, product, and quotient of these functions, pretty simple, right? You just combine them, right? So you literally just add them. Okay, so you have 1 over x minus 2 plus square root of x for the sum, and then the difference is going to be 1 over x minus 2 minus square root of x, and then the product is going to be, right, these two functions multiplied together, so it's square root of x over x minus 2, right? Pretty simple. And then the domain for all these three, it's going to be the same, right? It's going to be the exact same thing as we calculated earlier. The quotient, however, right, the domain is different, but yeah, the quotient is nothing too fancy, right? It's just 1 over x minus 2 divided by square root of x, right? So, right, that'll be in the denominator. So that's your final answer for that. And then, yeah, just note that, right, g of x can't be equal to 0, right? So g of x in this case was the square root of x function, right, as we see here. So that can't be equal to 0. So we just have to exclude that. And that they explain that here. So in the domain of f divided by g, we exclude 0 because that would make square root of x 0, right? Square root of 0 is 0. Okay, so just change that here. So that's the only difference, right? So here it's greater than or equal to 0. Here it's greater than 0. All right, part B, just as a reminder, the question was asking for f plus g of 4 and then f divided by g of 4. Okay, pretty simple, just plug in number 4 and then evaluate. Okay, so f plus g of 4, I have all the 4 parts, but we're only going to go over the first and the last one. So f of 4 plus g of 4, just plug in 4, right? So f over 4 minus 2 plus square root of 4. So that's 1/2 plus 2. Okay, 1/2 plus 2, that's 2.5, which you can write as 5 over 2. And then f divided by g of 4, you have 1 over 4 minus 2 times the square root of 4, right? We just use that function that we just found right here. So just plug in 4 here into that function. Okay, so we'll get 1 divided by 2. So 4 minus 2 is 2, and then 2 times square root of 4 is 2. So we'll have 4 in the denominator. So the final answer is 1/4. Okay, so 1/4 and 5 over 2 is your answer for part B. And then here was your answer for part A. Okay, if you need to copy any of this, please pause the video here. Here and here. Okay. All right, moving on to the next part. Okay, so I'm going to talk about the composition of functions, and for that, yeah, so before I get to the definition slide, let me just read what I would say to you in class. So composition of functions is the other half of our lesson for today. Okay, so let's try a new way of combining two functions to get a new function. Has anyone ever tried a cronut before? Okay, so a cronut isn't just a croissant and a donut. It's a croissant in the shape of a donut. So this is actually something that was really popular back in 2013, I believe it was. Dominique Ansel, which is, or Dominique Ansel's bakery is a famous bakery here in New York City, actually. And this pastry chef, right? So he made this croissant donut, right? Which is a cronut. Yeah, so this is like really popular. It's not just a croissant and a donut separately, right? As you can see from this picture here, which I'm getting hungry from, you get a, he made this donut with croissant qualities to it. Okay, so it's like, it's kind of like if the croissant and a donut had a baby and you get this cronut. Okay, so that's the composition of functions. Okay, I know it's a funny example, but that's how I would think of composition of functions. So If you see like the sum of functions like f plus g of x as the croissant plus the donut, so let's say you have that separately, right? You just have your normal croissant, your normal donut. Yeah, you can eat both of them. But for the composition of functions, you have a cronut, and you can eat this delicious looking thing, okay? Yeah, let me continue here. If you consider croissant and donut as functions, when you compose them, you wouldn't just get a croissant and donut. Okay, yeah, I basically said that already. You would get a cronut. And let me get to the definition here. Okay, so you do not have to copy this definition down. This is just the definition of a cronut. Okay, so a cronut is a croissant donut pastry that is made from croissant-like dough. Okay, it is filled with flavored cream and fried in oil to resemble a donut. Okay, so that's how I want you to think of the composition of functions. Okay, so it's a croissant donut hybrid, right? You combine them, you fuse them, right? They're intermingled. They're, you can't separate them, right? So that's the composition of functions. Okay, so with that said, let me get to the lesson, the remainder of the lesson. Okay, so here's the mathematical portion of this lesson for composition of functions. So suppose f of x equals square root of x and g of x equals x squared plus 1, and we define a function h as h of x equals f of g of x. Okay, so this should be familiar from the do now, right? Or you might, again, remember from algebra 2. Okay, how would you evaluate h of x? Okay, so first we just plug x into g, so this g function. This is a diagram from the old textbook. You get x squared plus 1, and then x squared plus 1 is now the new input for f, right? So then we're going to plug in x squared plus 1 into this function, so we'll get square root of x squared plus 1 as our output right there. Okay, so that's the composition of functions. And I'll just read the answer I gave here. Given a number x, we first apply it to the function g and then apply f to the result. In this case, f is the rule, take the square root, g is the rule, square and then add 1. So h is the rule, square then add 1, then take the square root. Okay, and you get h of x equals f of g of x equals f of x squared plus 1 equals our final answer, right, square root of x squared plus 1. Okay. All right, next I'll get to the definition slide. But if you need to copy this answer here, please do so now. Please pause the video here. All right, so here's the definition. And I believe this is the last thing before the classwork. All right, here it is. Yeah, here it is. Okay. So given two functions f and g, the composite function f, note that the symbol for composite functions is this circle thing here. F composed with g, also called the composition of f and g, is defined by f composed with g of x equals f of g of x. Okay, so the same thing written in two different ways. Okay, so you can write this as a circle here, or I find it more helpful if you write it like this, because that actually kind of tells you what you have to evaluate. But you can use either and just be familiar with both. And just note that the domain of f of g of x is a set of all x. So this is, I know this might be initially confusing, but we'll see that it's not too bad once we go through some examples. Okay, so the domain of the composition of functions of, using f and g is a set of all x that allows both g of x, and f of g of x to be defined. Okay, so we got to find where both g of x, the inside function, and the overall function are both defined. Okay, so that'll be the domain. Okay. All right, if you need to copy this, or if you need more time to copy this, please pause the video here. Otherwise, I'll be backtracking to the classwork. Okay. All right, here we go. So the classwork was as follows. So yeah, we have these questions. So we're going to use the composition of functions, and then we're going to evaluate. That's number 1. And then question 2, we're going to find the following functions and the domains. Okay, we're going to compose them. And yeah, that was what I was getting at earlier, right with the note. All right, so initially might be confusing, but once you see these examples, it won't be too bad. And then question 3, we're going to evaluate the composition functions of 3 functions. Okay, so you'll also see that this won't be that bad. Okay. All right, let me get to the solutions. Okay, so it's kind of long because there's so many parts, but bear with me. We'll get through it together. All right, here we go. Okay, here's the first question. Okay, so let f of x equal to x squared and g of x equal x minus 3. Find the composition of functions in both orders. Okay, so unlike the do now, this does matter. Okay, so yeah, here's the final answer for the first part, x minus 3 squared, and then the second part is x squared minus 3. So the order does matter here. And then we're going to find the domains, and then we're going to evaluate at 5 and then 7. Okay. All right, here's the solution from the textbook. So f composed with g of x. So we're first going to just take g of x. G of x is x minus 3. And we're going to plug that into f, right? So f of x, excuse me, is x squared, right? So we're going to plug that in. So we get x minus 3, that entire thing squared. So that's your answer for that first part. And then g composed with f, we get f of x first, that's x squared. And then we just plug that into here, right? So replace x with x squared, we get x squared minus 3. And that's your answer for that part. Okay. Part B, we just have to evaluate at specific numbers. Oh, sorry, I forgot the domain. Yeah, so the domains of both f composed with g and g composed with f are R, because there's no restriction here, right? Because g of x, right, it's a line, right? So you can plug in anything. And then the same thing for the composed function, x minus 3 squared, right? So remember, for the domain of a composed function, it has to be defined for both the inside function, here in this case, g of x, and the overall composed function, x minus 3 squared in this case. Okay, so here there are no restrictions, because you can plug in anything for x minus 3, you can plug in anything for x minus 3 squared. Same thing for this, right? F of x, x squared, you can plug in anything, and then x squared minus 3, you can also plug in anything. Okay, so the domain for both of these is the set of all real numbers. Okay, if you need to copy this part down, please pause the video here, otherwise I'll move on to part B. All right, part B. So f of g of 5, right, just plug in 5 for this function, so you get 5 minus, the way they wrote it was, so g of 5, right, you just plug in 5 into 5 minus 3, so you get 2, right? Then f of 2 is 2 squared, and that equals 4. Alternatively, you can just plug in 5 into this final function, so you get 5 minus 3 squared, so 5 minus 3 is 2, then 2 squared, right? Okay, same thing. Secondly, we have g of f, g composed with f of 7. F of 7 is 49, and then g of 49 is, where you used to just subtract 3, so it's 46. Okay. I actually like to see it, yeah, I actually like to see it as the way I did it earlier, right? Just, if you just plug in 7 into this final function, so 7 squared minus 3, right? I mean, we already did all the work, so why not just use it, right? So 7 squared minus 3, that's 49 minus 3, that's 46. Okay, but yeah, that's your answer for part B, right? Pretty simple. If you need to copy that, please pause the video here. Okay, moving on to question 2. Let me read this. You can see from example 3 that in general, blah, blah, blah. Remember that the notation. Okay, yeah, this is just saying that you need to pay attention to the order. Okay. Question 2. Okay, so here we have two new functions, square root of x and square root of 2 minus x. Okay, this question is kind of long because we have 4 different parts and we need to find the domain. And it's not trivial, right? It's not just a set of all the numbers. We actually have to think about it for a sec, okay? But yeah, let's jump into it. F composed with g of x. So g of x is this function, as I said, right? And then if you plug that into f, you get the square root of 2 minus x, right? So that's this thing here. So square root of 2 minus x, right? So if you remember from algebra 2, right? The square root of a function, you can rewrite that as that expression to the 1/2 power, right? So this is 2 minus x to the 1/2 power to the 1/2 power, right? So let me write that here. Right, so 2 minus x minus x. And sorry for my loud clicking. I'm using my laptop keyboard or my laptop mouse pad. So this 2 to x is the 1/2, and then that is the power of 1/2, right? That's that outer square root here. And if you remember your laws of exponents, right? If you have a power raised to a power, you just multiply the exponents. So you get 1/2 times 1/2, which is 1/4, which is how we get this thing. Okay, that's your final answer for that. Okay, and then, all right, the domain of f composed with g. So we first have to find the domain of this part, the inner function, right? And then we look at the composed function, the final composed function, and then see where they intersect. Okay, so the domain of this square root of 2 minus x is this, right? 2 minus x has to be greater than or equal to 0. All right, and then we can rewrite that as, right, just adding x to both sides. We get 2 is greater than or equal to x, or another way to say that is x is less than or equal to 2. So negative infinity up to 2. Okay. Now this, in this case, is actually the same thing, right? So once we found the domain of the inner function, we actually found the domain of the composed function, because 2 minus x to the 1/4 power, or the 4th root of that, you get the same thing, right? You have the same domain restriction. This radicand has to be positive or 0. So yeah, you just get this as your final answer. Okay, negative infinity up to 2, inclusive of 2. Okay. All right, part B. So this is g composed with f of x. So f of x is square root of x, and then g is square root of 2 minus that. Right, so if you remember, it's that part right here. Right, so just plug in this into that. So you get square root of 2 minus square root of x. Okay, and that's your answer for the composed function. Okay, pretty simple. Now the domain is a little more complicated. Okay, so for the inner function to be defined, square root of x, we must have x greater than or equal to 0. For the composed function to be defined, we must have 2 minus, sorry, this got cut off, 2 minus square root of x is greater than or equal to 0. That is, if you add square root of x to both sides, you get square root of x is less than or equal to 2. And then since we know that both these are positive, we can square them, right? If one of these were negative, then we have to change the sign of the inequality, but since it's both positive, right? So if you know that, like, for example, 1 is less than 2, if you square them both, then you get 1 is less than 4, which is still the same inequality, right? So yeah, we know that both of these are positive, right? Because square root of x can't be negative. And so we get x is less than or equal to 4, okay? So therefore, it's where these intersect, okay? So let me draw the number line here. So x is greater than or equal to 0. So that's this part here, right? And then the other part is x is less than or equal to 4. This is part here. And it's where they intersect, right? So it's between 0 and 4 inclusive. Okay, that's this final answer right here. Okay, 0 and 4 inclusive. That's your domain for part B. All right, moving on to part C. All right, part C was f composed with f. So we have square root of x, right? And then applied again, we get square root of x. Same thing with part A, we get the 4th root of x. And then, so that's your composed function. And then for the domain, right? Square root of x, the domain for that is x is greater than or equal to 0, right? As we know. And then that's the same thing here, right? So x to the 4th root of x, right? We have the same restriction, has to be, x has to be greater than or equal to 0, right? So just 0 up to infinity. Okay. All right, if you need to copy any of this, please pause the video here. So for part B, part B, pause the video here, and then part C, pause the video here. All right, and then lastly, part D. So G composed with G. All right, G composed with G is, so G of x is square root of 2 minus x, and then if we apply this again, so we plug this in to this function. So just take this part, right? This part, and then plug it into itself. So yeah, I know that's kind of meta. We get square root of 2 minus square root of 2 minus x, okay? So take that entire thing and plug it in for x. So substitute it with x, for x, I mean. So that's your final composed function. Okay. No, it was complicated, but yeah, that is what it is. And then for the domain, this expression is defined when both 2 minus x is greater than or equal to 0, right? That's that inner function here. And this inner, so the radicand, so this radicand has to be greater than or equal to 0, right? I'm just going to circle it, right? That has to be greater than or equal to 0, okay? And this has to be greater than or equal to 0. Okay. So the first inequality means that x is less than or equal to 2, right? If you just add x to both sides, right? X is less than or equal to 2. And the second inequality is if you add, so I'm going to add this to both sides, so this radicand. So you get 2 is greater than or equal to square root of 2 minus x. And another way to say that is square root of 2 minus x is less than or equal to 2. And then we're going to square both sides. So we get 2 minus x is less than or equal to 4. And then add x to both sides and then subtract 4. So you get negative 2 on this side. And then so you get negative 2 is less than or equal to x. Or x is greater than or equal to negative 2. Okay. So therefore, if you draw the number line, so that first inequality was x is less than or equal to 2. So that's everything here, right? And then this part is x is greater than or equal to negative 2. Okay. Greater than or equal to negative 2. That's that part here. So the overlap is this inside portion. Between negative 2 and 2 is where it's defined. So the domain is negative 2 to 2 inclusive of both values. Okay. All right, if you need to copy part D, please pause the video here. Okay. All right, and as I said earlier, right, this is not too bad. Yeah, just have to think about it a little bit, but yeah, nothing we can't handle, right? Okay. Last but not least, we have question 3. And that was the composition of 3 functions. So f composed with g composed with h. Okay, so just work inside out. So h of x is x plus 3. And we're going to plug that into g. So we get x plus 3 to the 10th power, right? That's this part here. And then we're going to plug this into f, right? So just replace x with this, x plus 3 to the 10th power. And we're going to get x plus 3 to the 10th power divided by x plus 3 to the 10th power plus 1. And that's your final answer for question 3. All right. This question was extra. Usually I wouldn't have time, but I think, yeah, let me just, it's pretty quick. Explain how f composed with g of x is different from f times g of x. So f composed with g of x is f of g of x, so this. And then f times g of x, sorry, is f of x times g of x. Okay, so it's just getting at the difference between the composition of functions and the other ways we combine functions. Okay, so that's, again, the difference between a cronut and having a croissant and a donut separately, right? I mean, in my opinion, the cronut is a lot better. You might beg to differ, but yeah, just know that it's different. Okay. All right. I believe that's it for today. Just a reminder to submit your homework. Right. That's right here. But yeah, thank you for staying on this long. I know this was a long lesson. Give yourself a pat on the back. And yeah, have a great rest of the day. And I'll see you all in the next lesson. Take care.